This is 5 minutes presentation of the paper, Robust Neural Routing Through Space Partitions for Camera Relocalization in Dynamic Indoor Environments. Camera relocalization is a fundamental problem in computer vision, graphics, and robotics. Given a set of posed RGBD frames as training data, the relocalizer takes a frame as input and infers camera pose. While state-of-the-arts have achieved high accuracy in static environments, they can hardly handle dynamic environments, which may include various conditions, such as object rearrangement and illumination change. It's difficult to cover all the dynamic conditions, so the relocalizers are mostly trained on the static scene, and tested on the dynamic ones. To address the aforementioned problem, we propose neural routing, a two-step algorithm to relocalize the camera in dynamic environments. In the first step, a neural decision tree infers robust correspondences between camera and scene. The second step optimizes the camera pose by fitting these correspondences. For the first step, we build a neural decision tree on scene space partitions. Specifically, we hierarchically divide the scene into K sub-regions. A four-way tree is shown as an example. In the tree, each node corresponds to a scene sub-region. Starting from the second level, we add an outlier route to each node. Now we obtain the Outlier-Aware decision tree. The tree infers an input point by routing it level by level until the end. Therefore, the point is either rejected by a certain level or falls into a leaf node. For each level of the tree, there is a shared routing function among nodes. The routing function solves a classification task, that is routing an input point to the next level. Specifically, it takes the point, its neighbor context points, and the current node information as input, and outputs a route path to a child node. The routing function is implemented as a neural network. Points RGBD features are extracted by MLP. Node information is integrated by a hypernetwork. At the training stage, since the scene is static, we train the routing function to memorize the correct route. By misrouting a point, we simulate the dynamic change as a negative sample. The routing function learns to reject such samples. After training, the routing function learns the scene with respect to each node. If a point is inside the region, the function routes it to a subregion. Otherwise, the function rejects the point as an outlier. At the inference stage, if there is no dynamic change, the tree infers the point to a scene region. If dynamic changes occurred, the tree rejects the point at some level. So far, we obtain correspondences between points from the camera and scene regions. Then, camera pose is optimized by fitting the correspondences. Specifically, we use the Kabsch algorithm inside Ransack loop. After that, we apply the ICP algorithm for pose refinement. In this figure, we show our estimation compared with ground truth. In the RIO10 dataset, compared with state-of-the-arts, we achieve the best score. For all the success rate metrics, we rank the first place. We also perform experiments on static scenes. We rank the second place. It shows the generalization ability of our algorithm on static scenes, though it is designed for dynamic environments. In conclusion, we propose a novel algorithm to infer camera pose in dynamic environments. It builds on three important blocks: the space partition, the neural routing function, and the outlier rejection module. For more details, please refer to our paper. Thanks for your attention.